Welcome to Alter Everything, a podcast about data science and analytics culture. I'm Megan Bowers, and today I'm talking with Naveen Krishnaraj, AI scientist at Sabanto. In this episode, we chat about creating machine learning models in academia and consulting, his work with AI in the agriculture field, and what makes him excited about future AI developments. Let's get started. Hey Naveen, it's great to have you on our podcast today. Could you give a quick introduction to yourself, where you work, where you're located for our listeners?
Thanks, Megan. I'm a big fan of the podcast. First of all, I want to say that about me. I'm currently a senior AI scientist at Sabanto. It's a tractor automation company. So we primarily focus on building autonomy kit for tractors. So that's my current role. I've been in the data space for close to 3 years now. And previously, I worked at a firm called Credera. I worked as a consultant there. And before that, I was in academia. I was a PhD student, and I got my PhD in petroleum engineering from University of Houston. Also did my master's there as well. And yeah, that's my whole short journey.
Awesome. I'm really excited to chat today to hear more about that journey and all these different experiences that you've had with machine learning and AI. So I'd love to just start off with your background in academia and research. Could you tell us a little bit more about that?
Yeah, absolutely. So I did my master's and PhD from University of Houston, like I said. In terms of my research background, right, I was working on signal processing behind NMR, nuclear magnetic resonance. So this is same physics as MRI. So I think everybody who goes through MRI scan at some point in their life, right? So this is the same exact physics, but we use it in a different setting. And I was a petroleum engineering department. So what we use it there for is, in an ideal scenario, we use it to detect oil and water, how much oil we have and how much water we have, and like other types of things in the reservoir. So that is the main reason or value of this work. I primarily focused on the processing side of things. So that was the overall work. And in terms of the motivation for the work, why we actually got, so it was actually initially a small part of what I was supposed to do. But then it turned out to be a whole thing, which I spent 6 years on. So the reason for us was we were using two different processing software for this NMR, and both of them gave us different answers. So we were intrigued and we wanted to understand why it's giving, and we went and dwelled deeper into the problem and understood what it's doing on the back end, and really go dig deep into the math part of it. And master's work was more about defining the overall problem. Got an opportunity to work with really smart scientists and professors at University of Houston, and really was able to dig deep and understand the problem and frame the problem better. But we didn't really invent or develop anything novel there. But then PhD work was more about developing a technique to solve the issues which we found during my master's work. And we developed a technique for joint inversion and unsupervised learning. So that's two technical words, right? I'm going to explain what it is. Inverse problem is everywhere. Inverse problem is throughout our life. GPS processing is an inverse problem. Basically, it's receiving some signals and calculating a position, right? And there are various other CT scan is an inverse problem. So inverse problems are everywhere. And unsupervised learning is basically it's a clustering problem. Again, that's everywhere around us. What we did was we developed a technique which combined both these inverse problem and unsupervised learning and solve it in a single step. This way we saved a lot of compute and we were able to generate a lot of practical use out of it. We saved a lot of compute and we also increased accuracy in various different cases. So it's a fun, interesting problem, but this gave me the fundamentals to go from end to end, go into the details of mathematics. So that was the whole fun part of it.
That's really interesting. And how long did it take to develop that combination model that you're talking about for your PhD program?
To fully mature, it took 4 years, but the actual grind of the work was like 1.5 years. But there was a lot of things which didn't work before we were trying. It's always about trying and learning from them and pivoting. So it took some time, but I would say to fully mature, it took 4 years, the whole suite of the PhD. and still a lot of things to do, but I graduated and got out.
Gotcha. Yeah, and so after academia, you moved into consulting, like you mentioned earlier, where you had to deliver these models much faster. So, what did that shift look like for you, and how did you navigate that challenge of having to deliver a lot faster?
It's certainly challenging. I would definitely acknowledge that. It's a whole mindset shift. So in academia, like you already asked me, it took 4 years to fully develop and mature something, and you are developing something novel, and things don't get out until it's fully refined, and you're pushing the knowledge edge a little bit. You're not really like changing a lot of things, but you are definitely adding something small to the research community or the scientific community. So that's what PhD or academia is about. But like moving into industry and moving into more applied machine learning or like consulting where I started out, it's a totally different mindset shift. You don't have 4 years to solve something. You have only few months and you need to generate value. So that is a whole mindset shift. There were the only way to learn is to by making mistake, but you need to learn from them. So uh, build a lot of mental models. How do you approach a problem? What are your processes? You need to build that, and only best way to build that is to be surrounded by smart people, which I had the fortunate of working with some smart people at Credera, and also be able to learn from your mistakes and be able to refine your process. So those are the initial struggles. But you, in terms of background wise, you already have that. I already learned a lot of math background and stuff like that from the academia, but scale is different. So cloud computing and those kind of things, I had to learn that. So those were the challenges, and there were people to support us through the journey, but you have to also invest some of your weekends and keep learning. So that's the only way to do it.
Yeah, and I'm curious, I think there was an article published a while ago now about data science and about how you spend 80% or so of the time just working on cleaning the data. Did you find that to be true in your experience, or do you feel like that's changed over time?
Yeah, it depends on where you end up, but in any case, any role, you have to still clean the data and do a lot of data engineering work. And in my case, yes, that was a big difference. There, the research was primarily focused on developing the algorithm side of things. So you don't really deal with a lot of messy data, and the real data is always messy, and that cleaning up takes a lot of effort. But in an academic setting, we still tested it on real data, but we were able to get the data which initially simulate some artificial data and kind of work with that. So I wouldn't say 80%, but yeah, definitely close to that.
Makes sense. Now that you've moved into your current role as a senior AI scientist in the agriculture field, I'd love to hear about what kind of projects you're working on with AI. I think it's a super interesting application that probably a lot of our listeners haven't thought about before.
Thanks for asking that. Yeah. In terms of my current role, the field as such is ad tech, but our my primary focus is on automation, like routing problems. So basically, what are the optimal paths the tractor needs to take? So that is one of the problem which I work on, and also another problem which I work on is computer vision. So basically, developing state of the art computer vision models to be run on the tractor for it to detect and understand the scenes better, being able to detect objects. So that those are a couple of problems which I work on actively. But also there are other data work, like means putting in the pipeline and kind of ML ops work. So those things are part of it, but those are two high priority problems which we work on right now.
For the computer vision problem, you're designing these algorithms to help the tractors navigate the fields, or like what does it help the tractors do, and what's the value that people see out of that?
Absolutely. In terms of computer vision, like you said, one aspect is safety. We already have a system which is based out of infrared rays, and it's able to use, it's called IFM, and we are able to detect objects in the field, and we are able to stop or pause on that. But what we are doing with the computer vision is we are adding to that. We are adding one more layer of efficiency and safety, because the IFM sensor which we have cannot really differentiate different types of object, right? A computer vision algorithm can do. It can detect there is an object there, and it can issue pauses, and that is doing well. And we want to be able to differentiate those objects, right? We want to be able to identify if a human is coming or there's an animal coming. So those are the things which we are working on. And the main value is improving the safety and also the efficiency of the system. That's the overall workflow. And man, it's a continuously learning model. It's not like we put in something and then it's set. There are constantly different objects we are seeing in the field, and constantly the algorithm has to learn and develop more intelligence, I would say.
That's really interesting. And so does that in turn like help farmers increase their yield, or what's the value for people driving these, not really driving these tractors because they're autonomous, but controlling the tractors, I guess?
Yeah, for our customers, like I said, IFM sometimes has false pauses. So we are trying to eliminate that. For example, it picks up a bird and it can pause on that. So we are trying to eliminate some of those inefficiencies in the current system. And also, not that the current system is not doing very well. We have a lot of customer adoption, but we are trying to nudge the bar forward, and we are trying to improve the efficiency, and also like we are trying to improve the safety. For example, if there is a new object which is getting detected, can we pick that up with all our perception system? And not just computer vision, we are exploring other sensors as well, like radar sensor, and there are other sensors which we are exploring, and computer vision is a part of it. And the system is only going to get better with more sensors and be able to handle different environments very well as well.
So then more broadly, how have you seen AI change the field of agriculture while you've been working at this company?
Before joining Sabanto, I was familiar with like yield prediction, and I was familiar with people using weed detection algorithms to eliminate some of the weeds, and that's the computer vision side of things. And there are more general broader data science workflows just dedicated towards enhancing efficiency, and also like the yield of everything boils down to that, right? Generating more yield for the farmers. While at Sabanto, being focused on the tractor automation part, I've seen what other people are working on, and what kind of algorithms they are developing. A lot of the focus is on being able to do real-time computer vision and doing it on edge devices, and like being able to autonomize the machinery which they have, be it any kind of machinery, not just tractor which they use in agriculture. And also like predictive analytics, like predict what's going to happen in the future. Those are the things which I feel like people are working on it actively. The main constraint is the edge side of things. If you had to do it real time, it has to be on a remote location on an edge device. So how do you handle that? So that is the main constraint.
Can you define edge device?
So think of you are pretty much in a remote location in somewhere in Midwest where you have very little connectivity, and you cannot like upload the data to the cloud and get it back, and you have to react based on real time data which you collected there. So what edge devices help you do is to be able to process a lot of information on the location and be able to use that information, but it has to be resource constrained. It cannot consume a lot of power. It cannot have a lot of processing power as well, right? It doesn't have the same scale as a cloud. So it is a resource constrained environment. For example, we have a camera, it's an edge camera. It can process certain level of TOPS operations on the device. So you have to design a model based on the constraints which you have there. So based on how much data it can process in real time, based on what frames per second we need the data to be processed at. So those are some of the constraints.
Okay, that makes sense. It's interesting. I'm thinking of autonomous vehicles in a city area where there's great Wi-Fi connection and how you could do a lot real time with that versus this. It sounds like it's a lot more challenging to compute and model like real time when you are out in the agriculture fields.
Yeah. And I think even in autonomous cars, they do it on the device. So it
They
means
do.
because it has to take a decision in few microseconds, right? So and for example, it detects a person, it needs to stop immediately. So it doesn't have, I don't know, the going through the cloud and to bring it back would be inefficient. I haven't really looked into their infrastructure, but I think everybody's working on edge.
Yeah. Okay. So it helps with the speed of decision. And it makes sense with what you were saying on the safety piece earlier. If there's someone standing in the field or an animal in the field, it's got to make that quick decision and be calculated super fast.
Spontaneous, yeah.
Yeah. Okay. Super cool. So, given your diverse experience with machine learning, academia, consulting, now data science and agriculture, what makes you excited about the future of AI?
That's a question I think about a lot. I can tell you that first. Mostly because this is very dynamic right now, right? And it has changed quite a bit over the years. Currently, the where the gold rush is, right, means generative AI. Everybody is actually using generative AI, right? ChatGPT from image generation, multimodal models. That's where the current focus is, and that is I closely follow it. I closely keep learning all the tools and tricks, and it's very exciting, I can tell you that, and it is transformative to humanity in general, and you can see that from the Nobel prizes which people got for the deep learning has been recognized, and people are looking at it as a beneficial to humanity and scientific society in general. So that is something which I'm tracking in terms of like short term, see how the field is evolving. We are still in discussion of using generative AI in our product as well, and that is the current buzz. But there are still a lot of noise around there as well, and I'm just waiting for the dust to settle down and see where this is heading. Means is the LLM the only route or not? So that's one thing short term. Long term, my focus is on. I'm really excited about quantum machine learning, which is an intersection of quantum computing and machine learning, and that is more a long term thing which I'm keeping a track on, and I feel like that would significantly change the field and transform a lot of different industries like never before. So
Yeah, definitely. And what are the barriers that you're seeing right now to quantum machine learning? Like, what is standing in the way of seeing that realized?
yeah, there are. Let me talk about quantum computing a little bit, right? It is which is quantum computing in general is a little counterintuitive. So bits are the fundamental part of normal computing. There is either zero or one, right? That's the fundamental unit blocks of normal computers, right? Which we currently use. But quantum computers are a little different or significantly different, where there is a superposition between zero and one. If you have a qubit, which is like a superposition between a 0 and 1, so you can encode a lot of information in this qubit, and that is transformative in terms of using it for machine learning application. The reason for that is you can process a lot of information with a very little amount of qubits. But in terms of some what you asked, right, in terms of some of the roadblocks, there is the qubits itself. We don't have enough qubits working together in coherence to be able to generate value yet. I think roughly around 1,000 qubits is, well, I think IBM Candor system is around 1,000 qubits, but that's not enough. The qubits have errors now, and people are actively working on error correction algorithms, which would make them more effective. But in order it to be practical, we need millions of qubits or a particular error collection algorithm, which, for example, you can crack the RSA encryption with, I think, 4,000 qubits. The qubits shouldn't be noisy, but the current qubits are noisy, right? So we need millions of them to do error correction and be able to crack it. But yeah, that whole research environment is exciting, and means now it's not practical. It's all research. It's not applied. So just something I passionately follow and just track it. But I don't think it's anywhere close to being able to productized, and there are certain aspects of quantum computing which are being productized. For example, there is a company called D-Wave which is working on a certain type of quantum system which can be used for practical application. I've seen people use it for practical application, but the real actual full-blown quantum computer is a little far, and hopefully some breakthrough happens and the AI people will start using it like more actively.
It seems like that would be a huge breakthrough, similar in scale to if we were to get to artificial general intelligence. I don't know, I might put a poll on this episode to see which one our listeners think we'll get to first, but do you have a guess on what we would see first, whether it's like general intelligence from AI or quantum computing, or are they intertwined? Do we need one for the other?
I think we need one for the other. If we get something and breakthrough in terms of quantum computing, it'll help us get to AGI faster. But in general, it's gonna have both of them are gonna have a profound impact on humanity. But in particular, quantum computing, it will help us a lot in the coming years in terms of fighting climate change and being able to, for example, the Haber's process, which is a process of creating ammonia, which is one of the process which hasn't changed because we don't really understand the things at a deeper level, how the interactions happens. So the quantum computer, we'll be able to simulate like the quantum system much better. So we'll be able to optimize the processes. So that is one use case how it can impact humanity. You might be able to predict the weather better, or you might be able to control the traffic better. So there are tons of other use cases other than just machine learning in general. So that's something which really excites me, and hope somebody makes a breakthrough. I constantly keep a track on where the field is heading.
Definitely. Super exciting for me as well. And thanks so much for joining us today, Naveen. I know I learned some things from you, and it was cool to hear about all of your experiences in the data science field. And if people want to stay in touch with you, can they find you on LinkedIn, or what's the best place?
I'm really active on LinkedIn, so feel free to shoot me a message or connect with me. And thanks for having me, Megan. I really enjoyed the conversation.
Thanks for listening. To learn more about topics mentioned in this episode, head over to our show notes on alteryx.com/podcast. And if you like this episode, leave us a review. See you next time.